Welcome back. So the last time we were looking at partial derivatives, we defined what's known as the gradient of a function, right? If all the partial derivatives exist, the gradient is simply putting them all together as a single vector, nothing mysterious about it. Of course, why is it called the gradient? We'll see that in due course. And for students of machine learning and AI, this is a very important concept, and likewise even for pure math students. Now, in fact, we can ask a further question. Suppose the gradient exists at on an open set. Okay, the gradient at a point is the partial derivatives at that point. Suppose it exists for all A lying in an open set. Rather, it exists in a neighborhood of A containing A, let's say. Then we can ask about the derivatives of each of these individual functions. Then we can ask whether which is the partial derivative of these partial derivatives exist. That is, for example, we can ask whether this exists or this exists, and so on, right? So these can potentially be different also, okay? Just because, I mean, these have x and y doesn't mean they have to be same. Can potentially be different. Okay, these are higher partial derivatives, but we will deal with them soon enough. Okay, right. More importantly, in one variable calculus, differentiability implied continuity. Yeah. And how did that work, right? Because what is f of x plus what is continuity? This must be very close to 0 when h is very small, right? This is equal to times mod h, right? And by definition of differentiability, right, as h goes to 0, this goes to mod of the derivative. So which means by definition of differentiability, this is very close to the derivative, is less than, for example, 1 if mod h is small, right? So in particular, this is less than, by the triangle inequality, plus 1 times mod h if mod h is small, right? And as h goes to 0, this goes to 0. So by the sandwich rule, so does this. This is how differentiability implied continuity, right? Okay. Now naively, what would we expect? Naively, we would expect that if the direction, we would expect naively, without thinking too much, that if, let's say, if say the directional derivatives along all directions exists for all b, or even more naively, or even more optimistically, if the partial derivatives exist then f is continuous. And this is what we would hope, right? But this expectation is spectacularly false. So here's an example. Let's take xy xy square divided by x square plus y raised to 4 if x is not 0, and 0 if x is indeed 0. Right. If x is not 0, this denominator is certainly not 0, and so certainly on this region f is continuous by what we discussed earlier, because rational functions are continuous wherever the denominator is not 0. Now what happens when x is 0, right? The trouble is f is not continuous at x equals 0. Okay. This is a nice example because it tells you that, so naively what would you do? How would you prove that? So what does it mean to be not continuous? That means, that is, this limit is not equal to 0, right? Or it may not exist, or even if it does exist, it's not 0, right? So how would you prove this? So for example, if I take a sequence xn equals yn equals 1 divided by n, what would f be? If x equals y, this is x cube, right? And this is x square n raised to 4. Yeah. So as n goes to infinity, where would this go to? Right. Unfortunately, so I'll where would this go to as n goes to infinity? The trouble is it will go to 0, right? It does go to 0, unfortunately, because this goes to 0 faster than this does, so this dominates this, and this goes to 0 faster than this does. So this is not a good thing to try. And indeed, if you take x equals y, or if you take any such path, right, it's not really going to help. It's not going to work. If you take y equals mx, on all such paths you will go to 0. This is a nice example to illustrate how things can go wrong. Just because you go to 0 along lines doesn't mean that the limit exists. Indeed, for example, if we take this sequence, now what happens? What is xn, f of xn comma yn equal to? It is 1 by n times 1 by n, 1 by n square plus 1 by n square, which is half for all n, and it's not 0. Okay? So it is certainly not continuous. On the other hand, if you go back to this, in fact, all the directional derivatives exist for all v. Why? Because it's a rational function, right? And I mean, this is one variable calculus, right? So if you take a directional derivative, it's simply a one variable derivative of a certain function. That one variable function will be a rational function, right? They exist when x is not 0. Okay. So when x is 0, right? So it's not continuous at 0, 0, for example. So when x is 0, this is 0, right? So here also the trouble is, will the directional derivative exist at the origin, right? So will the directional derivative exist at the origin? So the directional derivative at the origin is limit as h goes to 0, f of 0 plus h times v, f of 0 divided by h. Okay, this is 0. What is this? This is also 0. Why is it 0? Because if you look at this, if you put if instead of x you put h times v1 and instead of y you put h times v2, okay, and we take the limit. So what we want to do is, let's go back. So this is not 0 on the nose, but what I mean is the following: the limit is 0. So if I take h times v1, h square times v2 square, right, and h square v1 square plus h raised to 4 v2 raised to 4, right. So to compute the limit, right, as we discussed, it is not, for this you simply need to know that h is not equal to 0. So if h is not 0, then this is the case, right, and if let's say v1 and v2 are not 0, v vector is not 0, because if v vector is 0, then it is trivially it exists and it equals 0, right. Right. So I mean, when v vector is 0, then it's 0 by almost by definition. Right. So what is this equal to? So you can cancel out h square and you'll get h v1 v2 square by v1 square plus h square v2 raised to 4. Right. So in other words, this right, and this divided by h. Okay, sorry about this. So this is limit as h goes to 0. I forgot to divide by h. Right. So what is this? This is v1 v2 square by v1 square as h goes to 0, provided v1 is not 0. Okay. What happens if v1 is 0? Well, in that case this formula is not valid. If v1 is 0, this is equal to 0 if v1 is 0. Why is, if v1 is 0? Why is that so? Because if you go back to this, what is h of 0 plus h times v vector when v1 is 0? Then x is 0. So the correct formula to use is 0 indeed. Okay. So the bottom line here is that the directional derivative at with respect to v at 0, 0 exists for all v. Okay. So this is a problem, right? So the directional derivative exists in all directions, and yet the function is not continuous. Okay. So in other words, the bottom line here is continuity is a very subtle phenomenon. So the trouble is, so derivatives along directions existing is not a good enough definition of differentiability. Okay. Right. So this is not a good enough definition of differentiability. That's the trouble. Okay. Going back to the previous example, just one little point that I would not want to note for the future, this one. Let me just recall what it is for you. It's this. 0 when x is 0. Just a small point, you can calculate the partial derivative with respect to x when x is not 0. You can compute the partial derivatives with respect to x and y, and I urge you to do it. It's simply a one variable calculus exercise, so I won't bother doing it in any level of detail. I'll just write it down for you. So this is 2x cubed y minus 2x y raised to 5 divided by x square plus y raised to 4 square, right? And when x and y, these are 0 at the origin, okay? when x, not even at the origin, when x is 0. Okay. So in other words, at the origin, this is 0, these exist and they're 0. However, the limit as xy goes to 0, 0 of fx of xy is not quite 0. Okay. If you compute this limit as x comma y go to 0, 0, then you don't quite get 0, right? Why is that so? Why is that so? I'll leave you to think about it. Okay. Why? Please actually see if the limit exists or not, and even if it does exist, whether it is 0 or not. This is a nice exercise. So the bottom line is, this function's partial derivatives exist, but the partial derivatives themselves are not continuous functions. Perhaps this has something to do with the fact that this has something to do with the problem. Right? The problem being the partial derivatives, the directional derivatives existing, but the function itself not being continuous. Okay, but we'll just put a pen on it and we'll just put it at the back of our minds. We'll return to this phenomenon later. Right? Why is it that one variable functions are continuous? Okay, why does differentiability imply continuity in one variable? In one variable, the reason differentiability implied continuity is because of this property, right? So as h goes to 0, this goes to 0 and this goes to this, right? So in other words, this is a crucial property to have, right? Before we define differentiability, keeping this property in mind, let us look at a couple of other examples which also illustrate some very useful phenomena, pathological examples if you will. So suppose you consider f of xy as mod x minus mod y minus mod x minus mod y. As an exercise, you can see that the gradient at the origin exists and equals 0. F is also continuous at 0. Why is f continuous at 0? This is not very difficult to see. This follows from the composition law. Mod x is continuous, mod y is continuous. So if you add continuous functions, you get something that's continuous. If you subtract them, you get something that's continuous. If you take a composition of a continuous function with another continuous function, you get something that's continuous, and so on. Okay, so it's easy to show this. This requires a little bit of a calculation. Why? Again, I urge you to pause your video and think about it. So in this case, the partial derivatives exist and the function is also continuous, and yet, if we sketch the graph of z equals f of xy in 3 dimensions, and I urge you to do it. If you want, you can ask, say, ChatGPT or Gemini to sketch the graph of this for you. Okay, you don't have to actually sit down and do it yourselves. You'll notice something very interesting. There is no tangent plane at the origin. Okay, why is this a big deal? Notice here, this is the tangent line approximation. In other words, the function is close to a straight line if it's differentiable. So morally speaking, a function of 2 variables must behave like a plane in R3 if it's differentiable, right? However, there is no notion of a tangent plane at the origin. I mean, basically what happens is, if y and x are equal and they're both positive, then what is z equal to, right? Z is minus 2 times x. right? And the trouble is z is minus 2 times x and it's not 0, whereas the partial derivatives are both equal to 0. So if there was a tangent plane, that should have been the plane z equals 0, namely the xy plane, and yet if you move along y equals x, you do not lie in the xy plane. That's the trouble. Okay? So in no sense is there a tangent plane at the origin, and that is also a problem. Okay? So merely differentiability implying continuity is not good enough again to call a function differentiable because of this weird phenomenon. Let me notice one more phenomenon before I define differentiability for you. Okay? Right. So notice this can exist and yet fail to be linear in V. That is, if I take this, this need not be equal to this. It's not obvious that we would even require it to be equal, but just pointing a little thing out. But here is an example: x cube y, x raised to 4 plus y square when x and y are not 0, 0, 0 when x at the origin. This is continuous. Y, please think about it, has this at the origin, y, and this is linear. Yet it does not have a tangent plane at the origin. Okay? Why? Please sketch the graph of this and see for yourselves. Okay? So it seems that it is crucial for a function to be differentiable. The crucial point is having a tangent plane. That is more fundamental than merely requiring partial derivatives to exist or directional derivatives to exist, or even demanding that directional derivatives exist and the function is continuous, right? Or even demanding that the directional derivative is linear, and so on. Okay, so all of this is motivation for the following definition. Okay, so the definition is as follows: let f be a scalar field and A be an interior point. Okay, that is, this open ball is in S where R is passed. Then f is said to be differentiable at A if there exists a linear map df subscript A from Rn to Rn to R, such that for all h less than R, this limit such that on the set, this limit f of A plus h minus f of A minus the linear map acting on h divided by norm h equals 0. Okay. Alternatively, we want to say that the so-called error term, right, this is f of A plus h minus f of A times this, right? This term, in fact, this error term goes to 0 faster, than h does. Okay? So this is just intuition. So what we are saying is, indeed, in a certain sense, f of a plus h is approximately f of a plus a linear map acting on h. Why do we want a linear map acting on h? Because that's precisely the definition of a plane in Rn. What is a plane in Rn? A plane is simply, well, what is a plane in, for example, R2? It's of this type, right? A plus bx plus cy. So it is some constant plus a linear map acting on xy. So a plane in Rn is simply some constant plus the graph of a plane is simply some constant plus a linear map acting on h. So this makes sense. The expectation that f of a plus h is approximately f of a plus the derivative, a linear map acting on h. So f is close to being a plane. Morally, you should think of this error, morally it should be of the second order, right? This is a first order approximation, so it should be second order. So when you divide by h, it should go to 0. It's not quite second order, but at least we want to preserve this phenomenon, motivated from a one variable calculus situation. Okay, this linear map is called the derivative of f at a. Sometimes it is also called the total derivative. So this linear map is called the derivative of f at a, or sometimes the total derivative of f. Okay, so it is, in fact, this is the correct definition of differentiability. So proposition, if you wish, dfa, if it exists, is unique. So there's only one linear map that does the job if there is such a map. Okay, so that's not difficult at all. There are two ways to prove it. So if L1 and L2 are two such maps, then indeed L1 of h minus L2 of h, right? What's this? You can multiply and divide by h. Yeah, right. You can add and subtract and use the triangle inequality to conclude that this is less than f of a plus h minus f of a minus L1 of h and f of a plus h minus f of a minus L2 of h divided by h. Right. Okay. Right. So this is less than epsilon times norm h if h is small enough. Right? Of course, that's the definition of differentiability, more or less. Okay. Right. So in other words, L1 minus L2 h is less than epsilon times h. Okay. Right, but these are linear maps, which means for all norm h less than delta, L1 minus L2 acting on any vector v is less than for all v. Why? Because you can simply scale up the v or scale down the v. If norm v is not less than delta, simply keep multiplying it by some number to make it less than delta, and the left and right hand sides don't change. And this is true for all epsilon, which means L1 equals L2. If it's true for all epsilon, that means L1 minus L2 v, norm of that equals 0. But if it equals 0, then L1 of v equals L2 of v for all v. Okay, so this is one way to prove it's unique. right? Here is another way to prove it's unique. Let f be differentiable at an interior point A of the domain with derivative df. Then, interestingly, the directional derivative exists for all directions, and this linear map is exactly the same as this one, okay, which is also the same as the gradient of f dot product h, which is df by dx1 at A times h1, df by dx2 at A h2, and so on, df dxn at A hn. Okay. So, if the function is differentiable, then this linear map is not only unique, you can find a formula for it, namely this. Okay. Right. So, in other words, if you know the if you know the partial derivatives, which is just a finite collection of numbers, you know the directional derivatives in all possible infinitely many directions. This magic is accomplished when the function is differentiable in the sense that we defined. Okay. All right, we are out of time, so we'll continue the next time. Thank you for joining.